Okay, welcome everyone. Welcome to this Jones seminar on a sunny Friday afternoon. Thank you for coming indoors for an hour of good discussion. Today we're really happy to have Lorenzo Torresani come all the way across campus from the other side of the Dartmouth campus to visit us and tell us about his research. He's an associate professor of computer science here at Dartmouth. He has his laureate degree in computer science, summa cum laude, from the University of Milan, Italy. From there, he did his master's and PhD in computer science at Stanford University, finishing in 2005. Since then, he worked at several industrial research labs, including Microsoft Research Cambridge, Like.com, Digita Persona. His research interests are in computer vision, machine learning. He's a recipient of several awards, including the Computer Vision Proceedings Best Paper Prize, National Science Foundation Career Award, Google Faculty Research Award. He teaches multiple classes here, computer vision, machine learning, deep learning, and I have to say in the imaging space that I'm in, every student I talk to takes his class or wants to take his class. Even if they don't need it, they take his class. And it's been oversubscribed, so he's a highly desired person to associate with and learn from, and it's a pleasure to have him come across campus today. So thank you.
Thank you, Brian, for the nice introduction. So although my office is not too far from here, I don't get to visit there as often as I would like, so I appreciate very much the opportunity to be here today to talk about my research and hopefully also to strike some long-term conversations with Thayer faculty. So, as Brian mentioned, the field of my research is computer vision and machine learning. And today I'll be talking about the topic of learning computer vision models using large collections of big weakly labeled data. And I'll explain what that means later. But let me start, first of all, by describing what computer vision is about. So at a very high level, the objective of computer vision is to design systems that can automatically understand and interpret imagery data. Now, there are many different tasks in computer vision, but broadly speaking, we can categorize them into two main branches. On one hand, we have techniques that aim at extracting semantic information from the image. For example, methods that try to name all the objects appearing in a given photo. On the other end, instead, we have techniques that try to recover 3D geometry of the scene from, say, a picture or a video. For example, one of the projects I'll be describing today is about depth estimation from single picture, which means that given a single photograph, we aim at estimating for every single pixel in the picture the physical distance of the scene point that gets projected at that particular pixel. Now, these tasks are effortless to humans. We do it all the time. However, it's really difficult to mimic these abilities in machines. And in my view, the primary challenge in designing computer vision systems is that, well, if we want the system to interpret automatically the image, then we must first tell the machine how the visual world around us looks like. For example, if we want to build a system that can recognize automatically the presence of chairs in that particular photo, then we must first tell the machine how chairs look like in terms of shape, color, appearance, and texture. So what this means effectively is that we need to build a model for everything that we want the machine to recognize or measure in the photograph. So then the question is, how do we build these models? So in the early days of computer vision, these models were actually painstakingly hand-constructed. But over the last 2 decades, research has shown that much better models can be obtained by learning them automatically from lots and lots of image examples containing labels. So these training datasets typically are annotated with so-called strong or rich labels. These rich labels, in a sense, convey the information that eventually we want the machine to be able to predict, even on novel photographs. So in a sense, here's how we operate. First, during a training stage, we teach the machine to perform the task by showing lots and lots of image examples, which are annotated with the correct answer, so that eventually the system will learn to do the right thing. So where are these labels coming from? Well, typically they are provided either by human annotators, or they are captured automatically, but by using auxiliary sensors, depending on the task at hand. For example, in the context of image recognition, it is customarily to train systems literally on millions of photographs, where in each photo, human labelers have marked, using bounding boxes or free-form boundaries, all of the objects appearing in the photograph. And you see some examples of manual annotations here in this column, where each color represents a particular kind of object that we want the machine to eventually learn to recognize. In the case of depth estimation, instead, systems are typically trained on datasets of RGBD photos. These are photos that are captured with specialized depth sensors, which can measure not only the color in the scene, but also the depth of the scene. These are sensors like Microsoft Kinect. And some examples of color photos and corresponding depth estimated by Kinect are shown here. So it's clear that regardless of whether we rely on human labelers or specialized devices, collecting all of these labels is incredibly time-consuming. In many applications, it is so time-consuming that we can really manage to do it for constrained scenarios. So, for example, in the case of image recognition, typically we can do it for a few classes really well, but it's difficult to extend these approaches to recognize all of the visual classes that humans are capable of immediately recognizing. In the case of depth estimation, the same thing happens. Typically, people collect their training data on a few constrained environments. But what that means is that we end up with models that are also constrained and specific and cannot really capture the diversity of our real visual world. So today I'm going to talk about a different approach, which aims instead at learning automatically visual world models by relying exclusively on large collection of weakly labeled images. So images containing only weak labels of this form, describing essentially only the class of the picture, such as, for example, the kind of scene, or perhaps the primary object present in the picture. So only one label per image. So obviously, getting these labels is much cheaper than collecting manual regions or using specialized sensors. And there are already hundreds of millions of photos that we can exploit in this fashion. So today I'll show that we can leverage these large collections of weakly labeled images to build a comprehensive knowledge base of the visual world, which we can then apply to solve hard computer vision problems. So in this talk, I will focus on two primary applications. The first is recognizing and localizing objects in images without relying on manual region annotations. Then I'll discuss a technique that performs depth estimation with accuracy superior to the state of the art, despite using a very small training set of RGBD photos, but using lots and lots of weakly labeled images. And then at the very end of this talk, I will make a digression from the weakly supervised learning theme of this talk, and I'll just mention a few other projects which may be of interest to you. So let me start with the first topic, which is object detection. Object detection means essentially recognition and localization in images. But we want to do it without relying on manual annotations, and that's the reason we call it self-taught object localization. So this portion of my talk reports on joint work with Lorenzo Bazzani, who's a postdoc in my lab, Alessandro Bergamo, who completed his PhD last summer with me, and Drago Anguelov, who's a close research collaborator and friend at Google. So there are lots of cool applications of object recognition, but the primary motivation for me stems from the simple observation that over the last decade, we have witnessed a tremendous explosion of image repositories on the web. For example, it is estimated that photo sharing sites such as Flickr or Facebook grow at the astonishing rate of several 100 million new images per day. Every minute, over 50 hours of videos are uploaded to YouTube. And unfortunately, only a very small portion of all this data is actually annotated with text. Even when tags are available, they often do not describe accurately the actual content of the photo or the video. What this means is that we have this gigantic image collection that is continuously expanding, and it's just sitting there. Nobody can retrieve anything from it. Nobody can search in it using traditional text search technology. So I'm interested in designing recognition systems that can take a picture or a video and automatically tag it with its content so that we can enable text search on these important repositories. So here is how my ideal visual recognition system should perform, even on a challenging, complex scene such as this one. Should take this photo and automatically parse it into all of the objects that appear in it. So you should be able to recognize, for example, that these blue circles contain pedestrians. These pink ellipses include all instances of cars, despite having different color, scale, and orientation with respect to the camera. Same thing for the buildings. So how do we build a system that can perform this semantic parsing of the image? Well, here is the traditional approach. Well, traditionally, we build an object detector for every class that we want to recognize. So an object detector is essentially a classifier that takes as input a candidate region in the image. And then it says yes or no, depending on whether it believes that the region contains the target object or not. Typically, these classifiers operate on individual regions of the image. The reason we want this is because in this fashion we can factor out all the background, all the clutter, and all the multiple objects that are possibly present in the picture. But this means that, well, in order to train the classifier, we must provide lots and lots and lots of region examples. Positive examples, in this case containing cars, and negative examples, which are regions that do not contain cars. And this is typically done by hand. Then once we have collected these typically thousands of examples, or in some cases hundreds of thousands of examples, then we train simple binary classifiers such as support vector machine that discriminates the positive class from the negative class. Once we have achieved all of this, then detection is easy. It's just a matter of sliding this region classifier over all possible regions of the image. And there are smart search techniques that allow us to run a detector for a given class in a tiny fraction of a second, even on high resolution pictures. But it's clear that there is an inherent scalability problem with this approach. So this reliance on human labeling means that it's very painful to actually train a detector. And we cannot really do it on many, many different classes. I argue also that regardless of how careful we may try to be, or we instruct, say, Amazon Mechanical Turkers to be when selecting these regions in images, well, we end up with inaccuracies and biases in the sizes and locations of the regions annotated by the humans. So this means that the detector will not work perfectly. So in this talk, I will propose a different approach. So the approach that we propose involves, in a sense, taking a step back and considering a slightly simplified scenario. So we start from the task of whole image classification, which works differently from detection. So in whole image classification, the classifier takes as input a holistic representation of the image. For example, a feature vector that is computed by considering all of the pixels at once. And then it's simply predicting the class of the primary object appearing in the photo. In this case, seagull. Now, the big advantage of whole image classifiers is that they can be trained using simply class-labeled images, so weakly labeled images. They don't require manual annotation. The downside, however, is that well, they typically are not as robust as detectors, precisely because they operate on a holistic representation of the image. So they get easily confused if you have lots and lots of objects or if there is clutter in the scene. However, here's the idea. Let's consider the simplified scenario where we have simple pictures consisting primarily of one or just a handful of objects. Now, what we propose is to take this whole image classifier that has been trained with weakly labeled data and turn it into an object localizer. So something that can actually determine automatically the region that is most likely to contain the object. If we are capable of doing this without strong annotations, then we are in a good position because we can take these object localizations and now use them as effectively annotations for training object detectors. So these are positive examples. And now we are really in a win-win position because we can train easily object detectors that are robust to clutter multiple objects, but in a fully automatic way without relying on human selections. Fundamental question is, well, how do we turn a whole image classifier that has been trained without location information into an object localizer? And the solution that we propose is actually quite simple, and it consists in studying how the score or confidence of the whole image classifier vary as we artificially mask out different regions of the picture. The intuition is that when we mask out a region that overlaps largely with the object, then the confidence of the classifier should drop significantly. Conversely, if we mask out a region that has nothing to do with the object, then there should be no significant change in the classification score of the classifier. So in a sense, we turn object localization into the problem of finding the region that causes the maximum drop in classification score when masked out. So obviously a fundamental aspect in our approach is the choice of whole image classifier. So for this project, we leveraged the high accuracy of a deep convolutional neural network, since the systems have been shown to be impressively robust to clutter and changes in scale and position of the object, despite being trained as a whole image classifier. So I don't intend to go into the technical details of the model, but I thought I would at least give some intuitive idea behind deep convolutional networks, because I will be using it for both of the projects that I'll be presenting today. So first of all, the word deep refers to the fact that this is a neural network consisting of many, many layers, up to 20 layers. So each layer takes as input the output of the previous layer. Each layer also consists of a set of neurons. A neuron is essentially a nonlinear function that is applied to a weighted sum of the outputs produced by the neurons in the previous layer. The weights in the neuron are learned automatically. So this is a particular form of network. This is called convolutional network because actually most of the layers are performing convolutional filtering. What this means is that they're applying essentially a learned filter or many learned filters over the feature maps produced by the previous layer. And they keep doing this one after the other. Only at the very end, there are two so-called fully connected layers, which are not convolutional. So this particular network that we have been using was designed by the team of Jeff Hinton at the University of Toronto, now at Google. And this was trained for about a week by the team of Jeff Hinton on a collection of 1.2 million images spanning 1,000 different categories. So this is a whole image classifier capable of recognizing simultaneously 1,000 different categories. And when this was introduced, it was a huge breakthrough in computer vision because it outperformed all previously proposed systems by a huge margin in terms of classification accuracy. So here we leverage the high accuracy and robustness of this network to perform localization. So here is an illustration of how we propose to do it. So here is a simple input image, just a toy image, represented by X. So what you see here in this pipeline are essentially the feature maps calculated at each convolutional layer. So each quadrant shows the response of a particular filter learned by the network. As you can see, some of these feature maps exhibit high responses for the region in the foreground. most likely because the filter that was automatically learned by the system was tuned to recognize that particular color or that particular texture in the image. So at the very end of this pipeline, you see this number. So that's essentially the probability as estimated by the network of seeing a goldfish in that particular picture. Effectively, the network actually produces a probability distribution over the 1,000 classes. In this particular case, this is the most probable class according to the network. But here is what happens if we gray out this region, which overlaps largely with the foreground. The classification score drops to 0.0002, so very tiny probability. And you can see that this happens because the occlusion that we have artificially introduced in the input gets propagated through the feature maps. Now you see that the high responses that we used to have are now zero values. So effectively, the occlusion becomes an area of inhibition because the network doesn't see evidence of goldfish anymore. So then the objective is to find the region B that causes the largest drop in classification score. So how do we find this region? Well, unfortunately, brute force search is not an option here because inference through the network is quite expensive. So we resort to a simple strategy, which consists in generating a small set of candidate regions, which we then rank according to the probability that they contain the object. So here is how we do it. So given the image, we first perform a color segmentation of the image, which decomposes the image into a set of segments, so a set of regions, such that each segment contains a set of pixels that are contiguous and have similar color. Typically, the segments are small enough that they do not span multiple objects. Instead, in most cases, each segment is typically a part of an object. And then we perform hierarchical aggregation of these regions into bigger segments. So at each iteration, we take all of the current segments, we consider all possible pairs of segments, and then we merge two segments if they fulfill the following three conditions. First, the two segments to be merged need to produce a large drop in classification score by the whole image classifier for the same class. So if that happens, then it means that these two regions are likely to be parts of the same object, and then therefore they should be. We enforce these two conditions because, well, empirically we see that most objects are visually and spatially coherent. So after we perform this agglomerative clustering, then we re-rank all of the candidate regions according to the score, in particular according to the drop in classification score produced by the neural network. So simple strategy. And we tested this approach on two datasets. The first is the ImageNet dataset. This is the same dataset on which the neural network was trained. So it includes these 1,000 classes that are recognized by the deep neural network. But we also tested it on the Pascal benchmark, which is a very challenging dataset. It's challenging for several reasons. First of all, each picture in this dataset is not meant to be a picture for whole image classification. It actually contains multiple different objects and also a lot of clutter. Furthermore, the 20 classes that are represented in this dataset do not correspond exactly to the ImageNet classes recognized by the neural network. So what this means is that when trying our approach on Pascal, the system is effectively trying to localize objects that it has never seen before, or at least it has not seen during training. So because of all these reasons, we actually did not think that our system would produce good results here, but you'll see that we were pleasantly surprised in the next slide. So then we measure the localization accuracy of our system, and for this we used the ground truth that is publicly available on the test set of this benchmark. The ground truth was collected by human labelers. And we measure performance in terms of precision, which is essentially the proportion of correct localizations normalized by the total number of regions returned by the system, where each localization is considered correct if its intersection over union with respect to the ground truth is above 50%. And this is a standard performance criterion used in object detection and localization. So here are the results on both datasets. The results are reported as a function of number of candidate regions returned by the system. So on the left plot, you see the ImageNet results. We actually present two different variants of our approach, which is indicated with STL, which stands for self-taught localization. So the red line is STLCL, and it's a variant of our approach where we use our method, but we provide the information about the class contained in the image. So we tell the method, look, we know the class. Here's the class of the object that you need to localize. And then the system is simply used as a localizer of that object. In the case of STLU, instead, we do not provide this information. So in this case, instead, the system needs to perform both recognition and localization. And in this case, it essentially uses the top predicted class by the network as the class label, and then it calculates the drop in classification score for localization with respect to that particular predicted class. And the remarkable results, at least to us, was that actually the unsupervised version of our approach, which operates on just the image without the class information, is as accurate as the other approach, which means that we can apply our approach without telling the system what the object is in the picture. The other thing to notice is that our system provides higher precision compared to all the previously proposed object localization systems, particularly for small number of regions returned. And this is actually the regime we are interested in using. The reason is that, remember, we are planning to use the localizations as training data for detectors. So in each image, we want to return no more than, say, 1 or 2 candidate regions that can be used automatically to train the detector. So we were pleasantly surprised by these results. And we were even more pleasantly surprised by the fact that it actually works even on the Pascal dataset, where it was not supposed to work. The reason it works, I believe, is because although these 20 classes are novel, they overlap enough with at least one of the 1,000 categories for the system to actually be able to recognize them. So here's the experiment that we wanted to do. So we now took the localizations automatically generated by our system, and then we use them as training annotations for learning fully automatically object detectors without any human intervention. So this column shows the mean average precision obtained by detectors trained for 200 different categories using our automatically generated regions. So the performance is 20.43. So the performance you would get by using manual regions, so regions selected by humans, would be 25.4. So there is a gap, but the gap is not huge. And keep in mind that, okay, this came at a huge cost in terms of human labeling. Whereas here, the system is actually doing everything fully automatically. It's learning the objects and localizing them fully automatically. We also compared our localization scheme to previous localization methods. We found that training detectors on other localization methods produce always worse results. Here is another illustration of the same experiment. In this case, we reported the accuracy of detection for each class separately. So we have 200 dots here, each dot representing a particular class. And for each class, we report on the x-coordinate the accuracy achieved when training the detector using manual annotations. And on the y-axis, instead, we report the accuracy produced on that class by training a detector on our automatically generated locations. So you see that there are actually a bunch of points that are above the diagonal here. These are all classes that are better recognized by detectors trained on automatic regions generated by our approach compared to manual annotations. So, to conclude this first part of my talk, I presented a scheme that performs self-taught or localization, and it exploits whole image classifiers trained without any regional annotation to get localizations that can feed the training of object detectors. It works remarkably well even on unseen classes or classes that do not overlap exactly with the training classes of the whole image classifier. Now, the experiments that I've shown for detection were actually carried out using a very simple linear SVM, linear support vector machine, as object detector. But we are currently interested in taking all of these automatically generated region and now feed them as training data to our deep convolutional network, so that we can essentially transform the original whole image classifier into a detector. And we believe that that will produce a significant boost in performance. So before I move on to the second part of my talk, I want to check if there are any questions about this first part. Yep.
I'm not sure if I understand if it's automatically recognizing objects, but you haven't labeled them. How is it returning the definition of that object? It doesn't have a language in which to return that. So does it label them somehow, and then what is the defining feature of that?
Right. So yes. So you're referring to this plot in particular, right? Where essentially we applied our approach on a data set that involves classes that do not appear in the training set of the classifier. So as I mentioned, we do not fully understand why it works so well, but we believe it is because there is enough overlap between these novel classes and the classes that the recognizer was trained to classify. For example, we know that in Pascal there is a class called pedestrian, which does not appear exactly in ImageNet. But in ImageNet we have, for example, basketball player. So this similarity is enough for the system to essentially recognize the presence of something that looks like an object and to perform localization of it.
And what does it call it? Like, what do you interpret if it doesn't know the word ball?
Right.
What is it referring to?
So it simply localizes it. So our system doesn't really recognize it, right? But the idea is that, okay, if you can do localization on any arbitrary image, and images that have been weakly labeled, okay, so if you want to, for example, build a pedestrian detector, right, so you would certainly at least label all of the pictures that contain pedestrian. And then you can bootstrap from it and train it.
It localizes it, okay.
Exactly.
Yeah, got it.
So it would seem if you're using whole images that the context could be very important. If I want to recognize the eraser on the blackboard, I might not recognize it when I hit focus on the blackboard. To what extent, in using whole images, does content slide its way in?
That's an excellent question. So I brought up the example of the basketball player. So it was probably not a good example for your answer, but it's a good example for your answer to your question. Because, for example, I remember that when we looked at the localizations of basketball player, we were a bit disappointed in the fact that sometimes it was actually firing on something that was not the player. Okay, and then we realized that, well, it makes sense. It was actually firing on ball, or it was firing on the basket, which was visible, right? So it was indeed using scene context. So that's a bit of an issue, right? I mean, it's good because it exploits whatever is meaningful and relevant for recognition. But if you want to do accurate localization, then you may need to perhaps refine a little bit more the training images by making sure that they truly only contain the object that you are interested in localizing.
Later, for identification, the context could be more important.
That's right. So that's what I said. So if your aim is simply high accuracy of recognition, then that's what you want to do. You want to exploit any cue, including context. So let me move on to the second project, which deals with the problem of depth estimation from single picture. And I'm going to present a technique that uses a small training set of RGB photos, but millions of auxiliary weakly labeled images to achieve really good accuracy. And this portion of my talk reports on joint work with Harris Bake, who's one of my current PhD students. So here is the problem statement that we are trying to address. Given as input a single picture of an arbitrary scene, we want to estimate its depth. In other words, at every single pixel, we want to estimate the physical distance from the camera of the scene point that projects at that particular pixel. Now, there are lots of applications of depth for computer vision and for other tasks. For example, it's obviously critical to estimate depth if we intend to build a robot that navigates in an environment, or if we want to build a robot that manipulates 3D objects. But it's also useful in computer vision scenarios. For example, recently, Microsoft introduced a depth sensor called Kinect, and it has been really an enabler of breakthrough computer vision results. For example, they show that when you actually provide depth channel as estimated by the sensor as input to computer vision methods, you can actually solve really challenging computer vision problems like 3D human pose estimation in real time. The problem, however, is that these techniques were using the depth estimated by the sensor. But the reality is that, well, most of the pictures that we take are just color pictures. They do not have depth information. So the goal of this project is to be able to take any arbitrary color photo and estimate its depth so that we can apply the breakthrough technology that you see here even to regular photos. So if we go back to the problem statement that I mentioned just a few slides ago, if we think carefully about it, it's clear that the task is actually ill-posed without further assumption, right? Because, well, a single picture does not give you enough geometric constraints to perform accurate 3D reconstruction. But at the same time, it's also clear that there are enough physical and statistical regularities in the problem that we can come up with a probable solution given a single photo. After all, that's what we humans do. We look at a picture, we can guess the depth at every single pixel. So, for example, we can exploit physical constraints that tell us that most objects have continuous smooth 3D surface. That simplifies a great deal the estimation problem. Or we can exploit statistical regularities. For example, we know that most indoor pictures share the So one way to capture nicely these regularities is by learning them from examples. For example, given a training set of RGBD photos collected with a depth sensor, we can try to learn these regularities. So the way we try to learn them is by learning a function, so essentially by performing regression. We learn a function that, given RGB image as input, predicts its depth. The input to this function can be viewed essentially as a vector obtained by stacking all of the pixel values and color values one on top of the other. This will produce a vector that is 3n dimensional because we have three channels, and n is the number of pixels. And then the output space is n dimensional because we need to predict the depth value at every single pixel. So the problem clearly is that the dimensionalities of the input and the output are huge, right? So even a medium resolution image contains over 1 million pixels. And the other bad news is that, well, current RGBD datasets are still small data. They're not big data. Okay, so the biggest dataset available for indoor scenes is a benchmark which includes 800 photos. And for outdoor scenes, well, we have a benchmark that is slightly bigger, but still certainly not containing the millions of photos that nowadays we are used to using deep learning. So clearly not enough labels to learn a mapping from such a high dimensional space to such a high dimensional output space. So the way we propose to tackle this problem is by leveraging a large collection of labeled images from a different but related scenario. So the domain that we consider is the domain of scene classification. And we exploit a dataset called Places that was recently introduced by the group of Antonio Torralba at MIT. This Places dataset includes 2.5 million photos. And each photo has been labeled with class information denoting the scene class. And the possible classes are 205. So even just by looking at these images, you can tell that this could be used, indeed, to learn the structure of the input space for our regression problem. And that's precisely what we do. We are not only using these images, but we are actually using visual features and models trained on these images. And the assumption is that, well, although the features have been trained to discriminate these 205 classes, we believe that they're also useful for depth prediction. And here is the reason why. What you see here is a visualization of some of these features that have been learned by training a system to discriminate these 205 classes on this gigantic collection. The features are actually neurons of a deep convolutional neural network. Actually, it's the same network that I showed you earlier, except that this time has been trained on recognizing scene classes rather than object classes. So each set of 4 images here represent a particular neuron in the network. And it shows the 4 images, or the 4 portions of images that produce the highest activation for that particular neuron in the network. So looking at this visualization, we can gain an insight about what the network has learned. And it's clear that each neuron has been trained to recognize a particular scene structure in the photo. For example, we see that this particular neuron recognizes the presence of a slanted skylight ceiling. This other neuron recognizes staircases, and so on. But that's precisely the kind of scene structure that we need to estimate in order to perform depth prediction. So based on this intuition, we propose to use as features for our regression problem the neurons obtained from this scene classification network. So in particular, we use as a feature vector the activations from the last convolutional layer of this deep network. After this, we have, again, as I mentioned, fully connected layers. We take this convolutional layer because it's the last layer of the network that preserves spatial information. After this, we have a spatial scrambling done by the neural network. This makes sense for scene classification because at the end of the day, you need to simply predict a label. But it makes no sense for depth prediction because for depth, we need to capture spatial information. That's the reason why we use activations from this particular layer. Okay, we stack them one on top of the other. That gives rise to a 9,000 dimensional, roughly speaking, vector. So that becomes the input to our regression problem. So we achieve, in this fashion, 2 fundamental advantages. First, we greatly reduce the dimensionality of the input space for our regression problem. So the regression becomes simpler. But furthermore, now we have much richer features to work with. Rather than working on raw pixels, which don't mean too much, we now work on very expressive features that tell us about the structure of the scene. The downside, however, is that the output space is still n-dimensional, where n is the number of pixels that, for which we need to predict depth. So still not manageable enough to be tackled with the limited RGBD training examples that we have. So what we need is, in a sense, an analogous mechanism of dimensionality reduction on the output space. And that's what we do. So we reduce the dimensionality of the output space by making this assumption. We assume that the depth map of each image can be expressed as a linear combination of a small set of depth bases, which you see here. Now, these depth bases, in a sense, capture the spatial structure in the scene or in the output space. And you can think of them as prototypical depth maps, automatically learned from the depth channels of our training set. Now, you could, for example, use PCA, principal component analysis, on the depth maps of your training set to obtain such a set of bases. We use something a bit more sophisticated, as I will explain in the next slide, for good reasons. Now, once we have learned these bases, then we can express any arbitrary depth map in terms of a linear combination of them. So essentially, we summarize the entire depth map into m numbers, these particular coefficients that obviously vary from image to image. Okay, so the depth bases remain constant, they are learned once and for all, and then the only thing that changes from image to image is the linear combination, the linear coefficients, okay, the mixing weights. Why is this useful? Well, because now, instead of having to predict the depth values of individual pixels, all we need to do is to predict these m numbers, where m is much, much, much smaller than capital N, the number of pixels. In our experiments, we actually used m set to 100, and we got very good results with it. So 100, much, much smaller than 1 million, which is the number of pixels. So now we have a manageable regression problem, which we can tackle. We need to learn essentially a regression function from a 9,000 dimensional space to a 100 dimensional space, which is feasible even with using the limited RGBD training examples that we have available. So note that this problem involves effectively two learning tasks, right? The first task is learning the depth base. It's crucial to couple these two problems together into a single learning problem. For those interested in the technical details, here's how we do it. So given our training set consisting of pairs of photo and corresponding depth, as for example collected using Kinect, we learn bases, coefficients, and a linear transformation from the scene classification features to weight by minimizing a single learning objective, which is shown here. So capital B is a matrix of depth bases. The T is a linear regression function implementing the function f, and W are the weights. Okay, so if you look at this objective, it looks complicated, but it's not that complicated after all. It essentially consists of only two important terms. Okay, the first term says, look, I want a set of depth bases that approximate well the depth maps in my training set. The second term says, well, what I want is also a function implemented by this transformation T that predicts the weights. So what this means is that if we are minimizing jointly this learning objective, then it means that we are actually trying to simultaneously solve for a depth basis that approximate well our training depths, but at the same time such that the weights in these linear combinations are easily predictable from our features. All right, so we tested this approach on the two benchmarks that I mentioned earlier, NYU V2, which is the indoor dataset, and Kitty, which is the outdoor dataset. And we tested it on the test set of these two datasets, which is obviously separate from the training set that we use to learn our model. So in this table, you see the performance. Again, we compare our depth predictions to the ground truth, which is in this case the depth measured by the sensors. And the numbers you see in this table are actually summarizing the performance of 4 different variants of our algorithm. So in the first column, you see the best version of our algorithm, which is essentially what I just described to you. And then these 3 other columns refer to variants, which essentially revisit some of the design choices that I just explained. For example, in this second column, you see the error that you would get if you don't use the depth basis model. If instead you try to regress depth of every pixel independently. Okay? Well, that means learning a regression function to a much higher dimensional output space, which results in inferior performance. This other column instead shows what happens if you untie the 2 learning problems that I described. If you first learn the depth basis, for example, using PCA, and then regress the PCA weights. That's not as good, by far, compared to our couple learning approach. And in this last column, you see what happens if we replace the scene classification features with object classification features. And in this case, we get also a significant degradation in accuracy. And this makes sense because object classification features are more local compared to scene classification features, which instead capture the spatial layout in the scene and coarse structure, which is fundamentally important for depth prediction. We also compare to prior methods for single view depth prediction, and we found that our system performs much better and on both benchmarks actually. The only method that approaches the performance of our system is the recently introduced deep network by Eigen et al. But this was trained using 136,000 additional RGBD photos, which have just been released by the authors. So essentially, this network was trained using a training set that was 150 times bigger. So we perform slightly better than this network, which indicates the importance of making the right modeling model assumptions, which sometimes is more important than simply getting more data. So here you see some predictions performed by our system. Here are 3 input examples. Here are the depths of these examples measured by Kinect. And this is the prediction of our system. And you can see that it manages to get the correct coarse depth map. And sometimes it actually can also get fine depth variations, such as, for example, those caused by the presence of these objects in the background, or by the bookcase, in this case, in the second photo. So, in summary, this technique performs depth estimation with state-of-the-art results. The key idea behind our approach is to transfer knowledge from a domain where labels are plentiful, which is scene classification, to a domain where, unfortunately, labels are still scarce, which is depth prediction. Now, for those of you interested in technical aspects, you can think of our approach essentially as a strange deep network consisting of two parts. One part, which has been lifted off from the scene classification network. We freeze the weight to whatever these other authors had learned. We remove a couple of layers, we attach new layers, which are tuned and optimized for depth prediction. This is the only thing that we optimize for. Now, one can argue this is suboptimal, and I agree. But this also suggests a natural improvement, right? So now we can take the weights obtained from scene classification and just use them as initialization to refine further the entire network. So in deep learning terminology, this is called fine-tuning, and it's a very trendy approach. So that's actually currently being tried by Harris, my student. And we believe that this will produce significant improvement. The software is not posted yet, but Harris promised to do it within a week. So check back if you're interested in this technique. So do I still have 5 minutes? Okay. So in this remaining 5 minutes, I want to just give a glimpse into a few other projects from my lab. So a large portion of my research today is devoted to analysis of video. So together with collaborators from the Facebook AI lab, we developed a deep network approach for action recognition. So you see the top 2 predictions for each of these short clips by our network right here. So these are test videos. These are not training videos. And next to them, you see the probability estimated by the network. So one unique property of this network is that actually it's doing convolution, so filtering at each layer in 3D. So it means that it's actually passing over the spatial locations of each individual frame, but also over time. And it learns just from raw pixels very cool features. And we currently have state-of-the-art results on most of the action recognition benchmarks. I'm also very much interested in the problem of tracking and reconstructing 3D geometry from video. Together with my collaborators, we introduced the first technique that is capable of estimating the time-varying 3D shapes of deformable objects without any model assumption. So this is now known as the problem of non-rigid structure from motion. And the unique property of our approach is that it solves for the 2D tracking of features in the video, but at the same time it's simultaneously learning a deformable 3D model of the object that best explains the 2D observation. So it's effectively doing 2D tracking and 3D modeling jointly. My lab has also worked on the classic problem of feature correspondence between, say, two views of the same scene. And we developed a technique that performs feature correspondence as a graph matching problem. For those of you familiar with graph matching, this is NP-hard problem, which means that typically we can't get the global. So I'll conclude by, again, acknowledging the contribution of my collaborators in the two projects that I discussed today, and also I want to thank the institutions at the bottom of this slide for providing generous funding support for this work. So this concludes my talk, and I'm happy to take questions. Yeah.
I'm wondering if you can learn anything by looking at what is chosen as the ref basis set. And if I were to do it as a person, empirically, I'd say, oh, well, following intersections of walls and floors and looking at the size of the chair here versus the size of the chair there would be important. But are there things like that that come out in your basis set?
They do. In fact, especially if you impose. Let's see if I can go back to the slide, the technical slide, since you asked this question. So yes, so especially if you impose this constraint. So this constraint is a sparsity constraint, means that what we are trying to do is to reconstruct the depth maps with as few depth bases as possible. So we found this beneficial, so that's the reason we use it, but it actually gives also better bases because it's effectively requiring the system to explain the depth map with as few depth bases as possible. And this means that typically you end up with bases that are kind of like exemplars, right? So in that case, you really capture, right, very intuitive structures of scenes. So indeed, presence of ceiling, walls, converging, and so on.
Very practical question here. On most large data sets, I expect no images are the same size. And how do you handle that? And how do you handle formatting your depth basis functions so that
Yeah.
you can use them on
Good question. Yeah, so these are the ugly aspects of deep networks. So typically people do crazy things like either fixed size 256 by 256, throws away the original aspect ratio of the image. I think in this particular work, what we did, we actually operated on crops of the image. So then you can actually keep the aspect ratio. And operating on crops of the image is effective because then you have effectively an ensemble of methods, right? So you can actually stitch together then the predictions from many different crops. It then tends to produce even higher accuracy.
What's the computational sort of intensity, computational burden of this? Like this kind of, is it fairly low, or is it big?
Yes, so good question. So yeah, so let me start from the first system that I presented. That's expensive. So it takes localization on an input image of high resolution takes about 20 seconds on a GPU system. So expensive. But again, we didn't put any effort in optimizing it. And it's also meant as a replacement for human annotation. So we don't care too much about whether it takes long, as long as it provides training data for free. The second system that I present instead is very efficient. So I think it takes literally just a few seconds to estimate depth from a picture. And also the training is actually quite fast. I think we managed to train the entire system in literally just a few hours on a GPU system. So the the background training of the scene classification network is expensive. That took about a week. Yeah. Yeah, I mean, these networks are trained using a simple technique, which is called backpropagation, which is just a slightly efficient version of gradient descent. So it takes many, many passes over the entire training set, and the entire training set is 2.5 million images. So that's the reason why the learning takes so long. But again, in most machine vision and learning applications, training time is not important or not so important. The important aspect is inference or application of test time. And both techniques, especially the second one, is quite fast at test time. Okay, thank you very much.